should be. All right. So I'm going to start with the basics. Can you guys see that well? Or is it like, all right. Oh, I write too small. Yeah. Okay, that works. All right, so simplifying this, what you do is essentially you're gonna write it in like the easier to read form of like the fractions instead of just square roots. And then what you're gonna do is you're gonna wanna distribute this. So your A is gonna be raised to the to the 1/2. This one's gonna be to the 1/4. And then you're going to want to subtract these. So you're going to, where is it? All right, you're going to do, and for B, this one's for A, this one's for B. So then you're going to, since this one's a positive, you keep A in the top. And then essentially, because this one's negative, B goes in the bottom. You guys get that? All right. So we're going to move on to 1.6 with the inverse functions. Wait. I should write bigger. So with inverse functions, all you really do is you just like switch out the x and y's, and then you solve for y again. So then this becomes our x. We're going to have to move the 1 over before we do anything. And then we square both sides. So then you get this, and then it becomes just moving all your terms over. What was I? All right. Any questions on that one? Okay. I know it's not like real calculus, but like, sorry, but it's like the fundamentals, really. Are you guys good? Okay. How about now? All right. All right, for this one, we're going to want to express it as a single logarithm. Oh no. So from our ln laws, we know that we can raise the fraction up to the exponent. So it becomes this. And then we can raise this fraction to all of these. It goes basically those. And then we can use more ln laws with the subtraction and adding. Essentially, all we're going to do is we're going to just end up multiplying and dividing them. So this one becomes multiplied by that one. And then this one's going to be divided. And then we can simplify this further because you can factor this. My handwriting's atrocious. So then we get cancel like terms. And so that's expressed as a single logarithm. There we go. Are you guys good? All right, so this question involves a graph, so I'm gonna have to draw this out. It's in 2.2. Yeah, close enough. All right, so it's a state the quantity of each if it exists. So the first one, the limit of x approaches 1 of f of x. Oh, by the way, this is a graph of f of x. So as x approaches 1, we go in from both sides, basically, and it's 2. It's kind of like the method that you use for limits whenever it's just a number. Go in from both sides, but if it's from the left, go from the left. If it's from the right, go from the right. So this one's from the left. So then, as we approach from the left, we're going to get 1. From the right, we're going to end up getting 4. And as x approaches 3 from the left and right, our fingers won't meet. So essentially, the limit doesn't exist here, since our definition of limit relies on the left side has to equal the right side for the limit to exist there. So since we don't meet, it does not exist. And then finally the function at 3, which you just, wherever the function exists at the point 3. So it is 3. Any questions? All right, moving on. All right, so determining the infinite limit. We're still in 2.2 of all right, so infinite limits are kind of weird at this point because we don't have our rules or whatever that we learn later on, like L'Hopice. So I'm going to approach it like we don't know L'Hopice or anything. And essentially what you can do is, since we're approaching 1, we're going to have to do it from both the left and the right. So from the left, we're going to be thinking of, it's easier to draw a number line sometimes. So from the left, we're going to be approaching numbers like 0.99999, and then from the right, it's going to be 0.1111, because we're going to be approaching the number 1. Well, actually, it would be 0.00001. But so we know that it's going to be infinity essentially, but we have to know if it's positive or negative. So if you plugged in 0.999, we would know that the top would still, like, this is still going to be a positive value. And from the bottom, it doesn't matter, it's squared. So regardless of what we're going to be plugging in there, it's always going to be positive. So then we just test the top again with the 1.001 or whatever, as close as possible. Don't do like 2 or anything, because if you move over a whole digit, you can hit another critical point and you won't get what you want, and it's really bad. So it's still positive, so then we can so we know that the limit is approaching positive infinity. And the reason why we know it's infinity is because of the fact that if we plugged in 1, we would get infinity on the bottom, and it doesn't exist. So you know it's going to be like an asymptote. All right, this one's a little bit trickier. So same deal though, starting off. We have 3 and we're approaching from the right. So we're going to be doing like something like that. So we know ln functions can't exist when they're negative. So it's probably not going to be negative in there anyways. So if we were to do like the 3.001 or whatever, we know we're going to end up with some decimal value because they're extremely close, but there's still going to be this remainder, like, I don't know. It's going to end up something like this, you know? So we get something like that. But with ln functions, since they involve exponents, they're they look like this. So it's going to be negative if there's a decimal. So if you have a decimal inside your ln, you know that you're going to have a negative value. So then you know that this is going to be approaching negative infinity. All right. So moving on to 2.3. More limits. One sec. Okay. So if you ever see a limit with this type of form, you should know right away to do the conjugate, because that's basically the only thing you can do here. You want to get rid of the square root, and you want to get rid of the h in the bottom. So you would get something like, double checking, yeah, 9. And then also do not distribute your h, because your goal is to get rid of that h. Because we have an issue right now. If we were just to try to plug in 0, we'd have 0 in the denominator. So it's still being multiplied by everything. So if we were to distribute it, we'd still have an h everywhere that can potentially turn our denominator into 0. So these cancel, and then we know we can cancel these as well. So and then now if we were to plug in 0 into our limit, we would just get, and that just reduces down to 3, and you get 1 over 6. Any questions? All right. All right, so for this one, we have two different fractions, and we're going to want to have just one fraction. It's easier to deal with. So we have to find the least common denominator, which involves multiplying this side by not t, just the square root 1 plus t. This is really messy. All right, and then it's kind of going back to this problem. We recognize this form again, where we have like a square root on the top, and there's like some whole number being subtracted or added by it. So we know to do the conjugate once again. But be careful with this negative sign here, because we have a square root. So keep parentheses around everything, unless you're like extremely confident, and then just go ahead and distribute immediately. But and these cancel, and the t's cancel, which was our goal, but we still have that negative. So then now if we were to plug in t equals 0, you just get which is just equal to negative 1/2. Any questions on this one? Yeah.
At the very beginning, what did you multiply 1 over t by?
Just the square root of 1 plus t. Yeah, the one thing to get them to have a common denominator. All right. All right, so find the values of A and B. So this question wants us to find the values of A and B that make the function continuous everywhere. It's given to us as a piecewise function. I'm pretty sure this question was on your guys' test. Oh, I already wrote that. X is greater than 3. All right. So approaching this problem, we're going to want to use our definition of continuity that we have, which is essentially written like this. As the limit approaches A from the left, and it equals the limit as A approaches from the right, then the limit of A equals F, basically. F of A. I'll also write it over here. All right, so for these, for the top one, our x is going to be less than 2. So if we're less than 2, we're going to be approaching from the left. So we set this one up with our limit as x approaches 2 from the left. So taking this limit, we can factor the numerator, which becomes so we can cancel out the top and bottom. So that way we can get the limit as x approaches 2 from the left. And then we just plug it in, so we get 4. And then what we're going to want to do next is, now that we're dealing with 2, we're going to want to do with 2 with the right. So we take the limit as x approaches 2 from the right of this function, since this function is valid when it's to the right of 2, which you can plug in immediately. It's a polynomial. So you just get 4a 2b plus 3. And you're going to want to set these equal to each other because we want to make this function continuous everywhere. So to force this to happen, we're setting the left and right equal to each other. So then we get that expression. And essentially we do the same thing but at 3. It's the same deal as before. You could just plug in 3. So we get 9a minus 3x plus 3. And then for the limit as x approaches 3 from the right, you're going to want to use the valid function for x to the 3 to the right. You can also just plug this one in. So you get 6 minus a plus b. So you're going to want to set those equal to each other. So you get 8a. Wait. Oh, oops. This is supposed to be b. So where was I? Ah, this is b. So that's 8a. No, wait, that's not. It's 10a. Ah. 10a, 4b, -3. Double checking. All right. Did I lose anyone, or are you all good? Okay. So now we just basically have a system of equation, and however you want to solve it, it's up to you. You can either use like substitution or something, but I'm just going to go ahead and solve it like where is my oh so now I'm gonna add, oh wait, no. Which one do I want to multiply by? Multiply by, which one did I use here? Yo, I messed up somewhere. I messed up in my algebra, 1 sec. It's supposed to be (10a minus 4b equals 3). Yeah. Then for negative wait, where did I pull that from? Ah, this is supposed to be a 4. Okay. I'm going to multiply the bottom one by -2. So I get -8a plus 4b is -2. And then I can cancel out these. I get 2a, 1, and a equals 1/2. So then I can choose, that's a 4. So I'm plugging it back into this equation that we found. So if a equals 1/2, it just becomes 2, 2b equals 1. -1, and b equals 1/2. All right, so those are the answers. Did I lose anyone? All right. Oh, sorry. Just tell me when you guys are ready, I guess. Yeah. That was from equating our left-hand and right-hand limit of 2. So when you take the limit from 2 to the left, you have to use this function, which comes out to be 4. And then when you take the limit from the right of this function, you essentially just plug in 2. And then it gives you 4a minus 2b plus 3, and then you just equal it to 4. Because you want the function to be continuous, so you're just finding where they're going to be equal from the left and right. Any more questions? All right. All right, so this question, it wants us to use the intermediate value theorem to show that there is a root of the equation in the specified interval. All right, so for this problem, sorry. We don't have a y, so we're gonna have to like make our own. So we move everything to one side and we just equate it to y. I'm actually going to rewrite it as, I'm going to move everything over the other way, so the signs are all going to change. So, for this, we're using the intermediate value theorem. So it states that if a function is continuous on the closed interval AB and is between, by the way, I abbreviate a lot, so if you don't understand something, just ask. And f and b, basically the y values at a and b aren't equal to each other. Then there's going to be some number that f of c equals n. Oh wait, that f of c equals n, then there is such a number, sorry. C, so that f of c is equal to 0. All right, so basically going through this, we're just going to confirming this or going through its hypothesis or whatever. So our a is 0, so we're going to be wanting to plug that one in. Which is equal to, what is it, -2? And then we're plugging in our b for y of 1. What is that? -1. Remember that e is equal to like 2.7 something something. So we still know it's positive. So we know that this is going to be some positive number, and this is some negative number. And since our f of 0, where was it, is less than actually being equal to 0, and is less than that, well, f of 1, we know that there is such a number where it's going to be equal to 0. There is. F of c equals 0. So to explain this a little bit more, what we're doing is we're using the theorem on the interval from like 0 to 1. So our y's can't be equal to each other, and so what we do is we find them first to make sure that they're not. So at 0 we got like -2, and over here we got 2 something, I don't know, e minus 1. No, it's actually 1 point something. And drawing a line between the two, like obviously we have a root as we go from one to the other. So we can say that there is a number c where our function is going to be equal to 0. Any questions? This would be all right. Are you guys good? Let's do that to yes. All right. So moving into like 2.6, more limits. Essentially, we're just finding the limit. Or we show that it doesn't exist. In this section, we haven't learned L'Hopice yet, but it would still work if you wanted to use it. It might actually be longer to use L'Hopice sometimes. So this is a limit to infinity. It's essentially like finding a horizontal asymptote. And what you do is you're multiplying by the highest factor in the numerator. So then we get, it should just like, those are going to cancel. So these cancel and these cancel. And we're going to be left with, I'm going to reduce all these terms too, so it becomes 1 over x plus 4 over x squared, 2 plus 5 over x minus 8 over x squared. And remember that, just some side work, that if you take the limit of infinity of a fraction, like 1 over x, it's going to equal 0 because your denominator is going to be increasingly large to the point where you're just going to sum down to 0. So if we're applying that, we know that this is 0, 0, 0, and another 0. And we get 3 over 2. The shortcut way of doing this is just recognizing your largest factors and just taking the ratio of the two. So like for this one, we see that x squared and x squared, and we just do 3/2.
What other limit laws are there in this section? So, for example, you mentioned that limit as x approaches infinity of 1 over x equals 0. What other ones do you have?
Yeah, it's not exactly a limit law, but 2.6. It just goes over, it goes also over squeeze theorem, which I'm going to do. But 2.6. It just goes over like x to infinities, really. That's what its main focus is. So this one's a limit to infinity as well. So it's like the same concept. But it's slightly more complicated because of that square root. What was that? Oh, yeah. Those are my infinities. It does look like a fish. All right, so so approaching the square root ones are kind of strange, but essentially think about if we just took the square root to the side, what you get. You get 3x, 6 divided by 2 is 3. So I don't want to skip too many steps, but you can think of this as like the shortcut I was talking about earlier with the factors, but you're going to have to use this term instead because of the fact of the square root. So the answer comes out to be 3. I'm trying to, if we were to prove this more mathy, we would do, for this, it's square root of, what is it, 6? Yeah. Yeah. And to kind of help you out, think about, focus on like the denominator because you know you're going to be canceling that. You're usually going to be canceling out that term. So you're going to be squaring it and then square rooting it to make it equivalent, because if you want things to be equal, you have to do the opposite of it at the same time. So we're going to be doing both. So you want to, when you're multiplying inside here, you want to use the square root of x to the 6 instead. So that way you can cancel out those like terms and get, what is it? X of 1 over 5. And like this. But on the bottom, you can just keep it normal. It's fine. And then you can reduce everything. Those cancel, those cancel. And this turns into 0, this goes to 0. And you just get square root of 9, which equals 3. Any questions? I know it's kind of confusing a little bit. Well, are you guys good? Yeah. Where is it? Guess it's still on this page. Okay. All right, so for these, it's like the same deal. It's just that you're going to be using e to the x as opposed to like 1 over x squared. So you're going to be multiplying both by 1 over e to the x. You get e to the x minus e to the x all over e to the x. 1 over e to the x. So this turns into 1. These turn into 1. Rewriting it. Minus 1. Plus 2. All right. So now I'm applying this affinity. It's just like where that equals 0. Instead, now we have e. It doesn't really change much because, in fact, it makes it go to 0 faster because it's an exponential. So we can just zero out these terms. And then we get negative 1/2. Any questions? All right. Squeeze theorem. So we're going to use squeeze theorem to evaluate sine of x over x. You should probably know what squeeze theorem is. So squeeze theorem is essentially if we have this inequality of 3 functions and with one of them in the middle, if we take the limit as x approaches some number of the left inequality and it equals the limit as that same number to the right inequality, then we can say that the limit as x approaches that same number for the middle inequality is going to equal their values, essentially, L. I forgot to write L, like right here. So you might be wondering how to do this because we have sine and we don't have 3 other functions. But sine starts from the 0, right? Ooh. So this is essentially what a sine graph looks like, right? Sine is naturally bounded between -1 and 1 when you don't modify it. So that's what we're going to use as our bounds. So if we have 1, well, negative 1 because it's less than, sine, and then we have 1 on this side. Now, but that's not the same thing because this is sine of x over x. But we can make it the same thing. All you got to do is just multiply the whole thing by 1 over x. So and now we have what we're looking for. So then we can just take the limit as x approaches infinity. And we know that's going to be 0. And then if we take x approaches infinity of 1 over x, we know that one's 0 as well. So since with squeeze theorem problems, you typically have to write out, since you're like proving a hypothesis, equals 0, then the limit as x approaches infinity of sine of x over x is also equal to 0. Any questions? Oh, yay. Definition of derivative. Oh. All right. Are you good now? I can guarantee this is going to be on your final, since this is what the whole class is based around. It's just definition of derivative. All right. Definition of derivative. Where is my work? All right, so we know the definition of a derivative is So to be able to take this derivative, we're going to have to find, it uses t, gross, t plus h, which is just going to be and I know I'm going to have to expand that, so might as well do it now before I have all this mess. So 2th times h squared. My t's look like pluses. I apologize. I'm essentially just going to distribute this -9 to this whole thing, which is going to be -18 t of h minus 9 of h squared. All right. So then we're going to set up the definition. should we cancel? Is there anything to cancel? No. All right. And then it's going to be subtracting this, so it changes their signs all over h. It's usually a lot neater to do these first and then do the fraction. And it's a lot less writing. So we can see that this cancels, and I'm going to keep going from there. All right. I feel like I'm missing something. Ah, these cancel. I didn't notice that. So then, now all of our terms on the top have h, which is our goal because we want to be able to factor it out. Because we have that limit as h approaches 0 on the bottom. So pull h out from the top. And you still get an h though. That's okay. You can cancel them out. And minus 9h. And now you can just plug in, and you get 5 minus 18t. And then, since you know how to do a derivative by power rule, we could just look at, we just take the derivative and double check. So that becomes 5, 18t. Yay. It's a lot less work. But you're going to have to show all of your work on the free response questions, so. Any questions? Okay. Where was I? 3, 4, yeah. All right, so since I already did a definition of derivative problem, and I don't feel like doing more, we just do normal derivatives. If you try to use product rule here, because you see that it's a function of two products, it's going to be a lot more work and a lot messier than if you were just to have distributed them first. Always try to simplify before you take a derivative. So then using power rule, so the exponent becomes 1 less, and we multiply by the original exponent. So it becomes 3x squared, and you multiply by the original exponent. You can just think of it bringing it down, and then the lower number is replacing it. So it's 8x3. Any questions? Oh. Oops. All right. So for this one, I can see people using quotient rule, but it isn't necessary, and I would avoid quotient rule because it's annoying. So let's try to factor this the best we can. We can split, if you want to say, this fraction because they all have the same denominator. But remember, if it was like, I don't know, x plus 2 over x plus 1, you can't, like, no, don't do that. Don't try to split stuff like that. So it still looks kind of messy, but it's not that bad. We can rewrite these using our exponent laws. So we know this is -1/2. We know all these are going to be -1/2 because it's in the denominator and they're being square rooted. So we can bring them up to make our lives a little bit easier. And we can simplify this a little bit more. This is going to become 1/2. Its exponent. Actually, wait. There was a square. So now it's wait. No. What am I doing? Yeah, it's 3/2. Because all you're doing, since you're multiplying, you're just going to be subtracting their exponents. So we're going to subtract their exponents. 1 minus 1/2 is going to be 1/2. And then this one's just going to, we're going to leave it as 3 -1/2. Keeping in this form also makes it easier to differentiate because you can kind of just see what your exponent's going to be. So applying power rule, we bring down the exponent and we subtract 1 from our exponent. So we're going to end up getting 1/2 up here. We bring down our exponent. We're going to get -1/2. And bring down our exponent again. It's actually negative. 3/2. -3/2. Wait. Yeah, sure. So we can reduce that. To 2. Any questions? All right. How am I doing on time? An hour. Okay. All right, so I'm going to do an equation line problem. Yeah, sorry. At the point. All right, so we're finding the equation of a tangent line. The form that we like for lines is point-slope form. And so to start this off, take the derivative because we need m. We don't know what m is. So, and we know slope is equal to our derivative. So if we take our derivative, not too crazy. All right, we still have this function, but we want to find it at that point. So we're going to plug in our x as 0. So we get, which is just going to be equal to 2. And then we're going to go back to our point slope form. And this is our x1, and this is our y1, because these are the original function values. We were just finding the slope when we did the derivative. So using the original function values equals 2, and we found our slope m, which is 2, and we equal that 0. So then we get is the equation of our tangent line at that point. Any questions? Yeah. They provide us with the point. They want us to find the, yeah. One second. All right. So, getting into more complicated derivatives, slightly. Is that good? Okay. Using the quotient rule here is fine, but I would never use it because I hate quotient rule. We could just rewrite this, and instead of it being a quotient, we can write it as a product using our awesome exponent laws. So then, if we were to take the derivative, product rule, I do like the first times the derivative of the second, which also has a chain rule. So for this, we take the derivative of e to the negative x, and with chain rule, you leave the inside alone, and e to the x derivative is just e to the x. And then we have to take the derivative of what's in the exponent of e to the x and multiply it by that. So the derivative of negative x is just -1, and multiplying by -1 is just a negative, so it just turns our value negative. So the first one times the derivative of the second, plus the second one times the derivative of the first. The derivative of x is equal to 1. So we're done. That's the derivative of that. Maybe I should do a quotient rule. All right. All right. So taking the derivative of this one now, quotient rule is unavoidable. So I have a little like mnemonic for memorizing it. It's like low d high minus high d low over low squared. So if we were to do this derivative, we just do the denominator multiplied by the derivative of the numerator, which is just 2, minus high. So just the numerator, d low, the derivative of the denominator, all over low squared. And then distributing stuff, so this is going to become 6 minus 8x, -4 minus 8x, 6 minus 8x plus 4 plus 8 and it reduces down to 10 over 3 minus 4x squared. Any questions on that one? All right. Wait, what was that? Okay. Okay. More derivatives. This whole class is derivatives. This time it's just chain rule. So it's a little easier to see if we write it out like this. Again, with chain rule, do not touch the inside on your first step, just the derivative of the outside. So anything like exponents, trig functions, e's, anything like that. So we're not touching the inside. And negative 2/3. And then we multiply by the derivative of the inside. And you do this for how many insides there are. There could be several composites within each other. So it just ends up being 4 because the derivative of 4x is 4 and the derivative of 1 is 0. Wait, what was that? All right. To show multiple like chain rules. Where was I? We have cotangent squared, and inside cotangent squared we have sine theta. So if we're to take this one's derivative, we do the outside first. It doesn't look like it, but the square of the cotangent is actually the first outside. So we move that one down. Now we take the derivative of the inside. The first one would be the cotan. So the derivative of cotangent is negative cosecant squared theta. And then we multiply again by the other inside, which is sine, which is just cosine. Any questions on this one? You try to move from the most outer thing, which the square could be written all the way over here, but usually you write squares for trig functions right on top of them. And then you take the derivative of the trig function, and then whatever is inside that trig function, and whatever is inside that, and so on. Mm-hmm. Mm-hmm. Oh, yeah, that's, might be. Wait. Yeah, it's supposed to be sine theta. You're right. Might be. Yeah. Yeah, she just said that. Oh yeah, it's sine theta. Sorry about that. All right. Ah. All right, so for this one, it's inverse sine. It's not sine to the -1. Our derivative for inverse sine is 1 over square root 1 minus x squared. You can use u sub here if you wanted to. Like you can just turn all this into u, or you can leave it as b. Just think of this entire thing as this x. So if we were to take this derivative, the most outer thing is the inverse sine. So you get 1 over square root 1 minus, because that's the form of arc sine. So then throwing in what's in the inside of arc sine to that x squared, and then we have to multiply by what's inside. So doing this aside, don't know why. And then we just multiply by that. So it'd be 2. Yeah. Any questions on that one? All right. Yeah. All right. So for a related rates problem, my favorite, we have the top of a ladder slides down a vertical wall. At a rate of 0.15 meters per second. At the moment where the bottom of the ladder is 3 meters from the wall, it slides away at a rate of 0.2 meters per second. How long is the ladder? All right. So with related rates questions, it's always good to start off with like a picture. Some visualization of what's going on and setting up like a coordinate axis. So we're given that the bottom of the ladder is 3 meters away. So we can mark here 3 meters. And we know at this point up here, the top of the ladder, we're moving down a vertical wall at a rate of 0.5 meters per second. And over here, we're going to be moving away from the wall at 0.2 meters per second. So, since we set up a coordinate axis, and with related rates, we know everything's going to be, typically everything, is going to be in with respect to time. And it usually gives it away by the units, meters per second. So you know you're going to have a distance divided by some time. So, since this is a rate, which typically means derivative, we could say this is our dy dt is equal to 1.5 because it's moving down our y-axis. For this one, it's dx. That's actually negative. Dt is equal to 0.2 meters per second. So, kind of organizing it a little bit, we have our knowns as x equals 3, dx dt equals 0.2 meters per second, and our dy dt is negative 0.15 meters per second. We can define as the length of the ladder as L. Doesn't really matter. So, we also have some equations we can use. We know an equation for relating the sides of a triangle. So, if we were to define this as our x, and this is our y, we can say that x squared plus y squared equals L squared. And what we want to find is L. So since we're given a bunch of rates, we know that these distances are going to be changing. So we take this derivative with respect to time. So we take our equation and we take its derivative with respect to time. So d dt of x squared plus d dt of y squared is equal to d dt of L squared. So taking the derivative of this, we get 2x dx dt plus 2y dy dt. This comes from our implicit, because we're going to take the derivative, we bring down the 2, so we get 2x, but then we're still going to have an x left over, and so we end up with dx dt. Where was I? Oh yeah, so then we get 2l dl dt. So now we have more unknowns, and we want to find them. So actually, these are known. We have these that are unknown. However, we know that the ladder's length's not changing. So we could set this equal to 0 since the ladder stays the same length. It has no rate and change. So we write dx dt plus dy dt equals 0. All right. So to find L in this equation, we need y. That's the value that we don't have. However, we just came up with this equation, and we have everything for this except for y, so we can solve for it. These are decimals. All right, where is my... What chapter, which section is this? 231. 2.7. Sorry, I'll keep going until I get to the decimals. So plugging everything that we know, we can say 6 We know dx dt is equal to 0.2 plus 2y, and our dy is negative 0.15 equal to 0. What section is this? 3.4. 3.4, 31. That's 3.9. Ah, there it is. One second, double checking everything. Oh yeah, we could just solve for L right there. So, all right, continuing on this. We can solve L with this equation right here. So L is going to be equal to square root of, actually not L, sorry, Y. Y is going to be equal to L squared minus X squared under that square root. I'm just doing this way because this is all in decimals, and I don't feel like pulling out a calculator. So, and our X is equal to 3. So then we move this over. Square 0.3 on the outside of the square root. Oh, wait. Yeah. I messed up my signs. I think I did. Y equals whatever. So this is going to be equal to squaring, then since now it's equal to 4 on this side, and now we can just square both sides to get rid of the square root. This is 16. We get, what's the right answer? Yeah, 25. And then L is going to be equal to 5. Sorry about that. Any questions on this?
Where'd you get L squared minus 1?
Here, I just kind of skipped a step. X is equal to 3, so 3 squared is 9. You can rearrange that. You can also just find Y and then plug it back in, but since there was decimals, and I did it in decimals here like that, I didn't feel like redoing it. I don't have a calculator, so. Is everyone good on that? All right. So, moving on to 3.10, we're going to find the linear approximation of f of x equals 1 minus x at a equals 0, and we're going to use it to approximate 0.9 and the square root of 0.99. All right, so our equation for linear approximation is this. L of x is equal to f of a plus the derivative of f of a times x minus a. And this problem, they provided us with a. So a is equal to 0. And we want to approximate these values. So if our function of x is equal to this, and the inside, so just equating the inside terms, we want our inside to look like this. So our x is just going to be equal to 0.1. So that's how we find our x term. And then from there, it's pretty simple. You just follow through with the form. So we want to do f of a first, which we know is equal to 0. So, and then the derivative of f of a, that's not negative, it's just 1/2. We're going to bring this down, and it becomes negative 1/2. So, and then if we plug an a to that, that just gives us 1/2. No. It's supposed to be negative. Oh, wait, that's negative. Oh well. Is it supposed to be negative? Huh. All right. So then, our L of x, or our, we found x. So now we plug that in, 0.1. F of a at 0 is 1. Yeah, it's supposed to be negative. Why is it negative? Ah, it is negative. Because the derivative of this, I forgot chain rule. The inside, not 1, it's 1. So we get negative 1/2. I was wondering where the negative came from. So f of a equal to 1. Derivative of f of a at a equals negative 1/2. And then we have x minus a. So x is 0.1 and a is 0. And that comes out to be 0.95, which is a pretty all right approximation. Any questions on that one? Yeah. Yeah, sorry about that. I took when you take the derivative, you also got to take the derivative of the inside because it's being square rooted. And since it's negative x, it becomes negative 1 multiplied by that function. I just forgot it. All right, is everyone good with that?
Will A always equal 0?
It's whatever they provide. Yeah.
So then, let's just say for all intents and purposes, it was at A is equal to 1. Will we change that problem?
It should. Let me think. Yeah, because then you'd be having f of a, if it was 1, it would be square root of 2. No, it'd be 0. So then, yeah, it'd change it. Everything would just be 0. All right. I'm so tired. All right. So we're going to verify if this function satisfies Rolle's theorems. And then if it does, find all numbers C that satisfy its conclusion. So we have this function, f of x, 5 minus 12 of x plus 3x squared on the closed interval 1 to 3. Whenever you do a Rolle's theorem problem, it's probably going to be free response. So you're going to want to write out as much as you can for all that partial credit. And Rolle's theorem basically states, 1, that the function needs to be continuous on the closed interval a to b. It needs to be differentiable on the open interval a to b. And f of a needs to equal f of b so that there is a number that is between a and b such that the derivative at that number will be equal to 0. Five minus 12. Yeah, sorry. You can essentially think of Rolle's theorem as like if you had 2 points on a graph and they're at like if they're at the same y value, other than a straight line, if you try to go to it, the derivative is going to equal to 0. Even on a straight line, it equals 0 because it's completely horizontal then. So like no matter which way you curve to it, you're going to have a place where the slope of your graph is going to be equal to 0. So we first got to make sure that it's continuous. Polynomials are continuous at infinity. So I know it's a polynomial, so therefore it's going to be continuous. And then differentiable. We could go ahead and take the derivative because we're going to need that anyways. So 12 plus 6x. All right. And then for the third condition, f of a needs to equal f of b. So f of a is 1. So that's 5 minus 12 plus 3, which is equal to 12, 11, 10, 9, and then we suck at math. And then we're going to do f of b. Don't know why I can't think. Where am I? Just 12 of 3 plus 3 of 9. Yeah. Yeah, -4. -4. And then, so we're satisfying every single condition. So now we can say that there is a number where the derivative is going to be equal to 0. And it wanted us to find that number. So all we got to do is just set the derivative equal to 0. Which is, 12? And then you get 2. So, yeah. Any questions on Rolle's theorems? A little bit of both. So like, you're going to want to take the derivative. And if you can take the derivative, it's obviously differentiable. I don't think you're going to have a function that's not going to be differentiable. It would only be not differentiable if it was, if there's any discontinuities you had to worry about, like at corners and, you know, point discontinuities and such, jumps. And we don't have any of that since we just have a plain old polynomial. What was I doing? So for this one, we're going to do something similar, but we're going to verify the mean value theorem. One of these will show up. It's either going to be Rolle's or mean value. I doubt both, but maybe. So mean value theorem is essentially f is continuous on A to B. F is differentiable on A to B. The open interval. And there will be a number C in A to B such that the derivative of C is going to be equal to mean value theorem is basically saying if you have a graph and you have 2 points and it's continuous and differentiable, you're going to have some point on this graph where if you were to just take the slope of these 2 points, you get something like this. And somewhere on this graph, you're going to have, on the actual function, you're going to have a tangent line that's going to be equivalent to that slope. So doing the same thing as before, it's a polynomial, so we know it's continuous. So it's continuous in all real numbers. There's no, it's not a piecewise function or anything, so we can differentiate it everywhere. So let's go ahead and just take that, which will give us 4x minus 3. And then now we are going to want to set our derivative of c equal to our interval. 2 is our b. F of a is 0. B is 2 minus 0. So we plug this into our function that was given. So f of 2 is going to be equal to 4 minus 3, 2 plus 1, which is going to be equal to 8 minus 6 plus 1, which is going to be equal to 2, 3. And then we're going to get, what was this one? A is 0, so we plug that one in, and we just get 1. So f of 2 is 3 minus 1 all over 2, which gives us 1. All right, so that's where, yeah. No, it was 2, so I already squared it. Yeah, sorry about that. So this is what the slope between these two lines are equal to. We want to find the c now. So to do that, we have to set the derivative equal to this, right? I believe so. Yeah. So should give us the same value. Where is it? There it is. So our derivative equal to 1, 4x equals 4, and then we get 1. Any questions on that one? 20 minutes. Christ. All right. All right, so for this one, we're just going to want to graph the function. They're just giving you a function, they tell you to graph it. I would start off by simplifying the function, so we can have a simplified form of that. Plus 4x and then third. All right. So our domain, it's being cube rooted. So we don't really have to worry about domain so much. If it was square rooted, it'd be a little different. But we can basically say that this is going to be continuous on all R, as are the range. You're essentially just looking for discontinuities and trying to find where they're at. All right, so since we don't have any discontinuities or anything, we want to find our critical points. So let's set this equal. Let's take the derivative of this, 4/3. Is that right? No, it's not. It's 2. We're going to set the derivative equal to 0. So that way we can find where our derivative is changing. So we're going to factor out. Gosh, the Chester's problem. The largest x. I think that's how we do that. What do we multiply by again? -2/3. 1/3. X is going to be equal to 1. Oh, okay. Wait, what? I actually don't have the solution for this one, so I might skip it. Not gonna lie. Or I might do a simpler graph. Yeah, I can do the graph of a simpler one instead. Oh, sorry about that. I just didn't have that one prepared at all. And I don't want to botch doing one. All right, so this one's easier since it's a polynomial. We know the domain is going to be all real numbers as well as the range. And we're going to be taking the derivative of it to find the critical points. So we'll bring down that 5. It's 4, and we get 5. And then we set this equal to 0. Equals 1. And then the fourth root of 1 is just 1. So we get x equals 0. That's where our slope is going to be equal to 0. We should probably also find where our function itself is going to be equal to 0. But I already took the derivative, so at x equals 0. So now we're going to want to plug in points to find positive or negative values. So we can plug in anything into the derivative. If we plug in 1, we get 1 to the 4th is 5. Wait, yeah, we get 5. What am I doing? That should be. Oh, duh. Sorry. Set the function equal to 0 first. How do I have to complete this? So let's expand this. No, not expand. I'll just keep going. Painting the square. I don't have any of the graph ones prepared, unfortunately. I'm sorry. I'm like trying to do these, but I'm way too sleep deprived. I hate final sweep. I'll come back to it at that time. I just want to move on. I don't want to sit there and get stuck. I'd rather cover more material. You guys could try these as extra practice on your own, but we only have, like 3 minutes left. So I wouldn't even be able to finish it, unfortunately. So for this, taking these limits, we're going to use L'Hopice. So for L'Hopice, you usually indicate when you use it by some sort of symbol. I just use an H over the equal sign. And when you use it, you just take the derivative of the top and take the derivative of the bottom. You don't do quotient rule or any other sort of thing. You just take them independently of each other. And you keep taking it until you can just plug in the limit, or you can factor. So can we plug in the limit now? We get 2 minus 1. I don't see why not. And we get 2. You could have also factored this, but this way was a lot faster. And I'll finish up this one. So for this one, we don't have the form that L'Hopice likes, where if you were to plug in, you get infinity or 0 over 0. So we have to make that happen. So it's sine pi over x, 1 over x. And then we have to take their derivatives independently again. Normally you're going to be doing it to the x values, and not the trig function. It would be cosine pi over x, pi, I believe it's like 1 over 2, or something like that. And then this is like squared as well. And try to go do this as fast as I can. Yeah, this one's negative as well. And it reduces down to actually the negatives cancel. These are actually going to cancel because this moves down and this moves down. This cancels. And you could just take the limit of that. All right. Because before, if you took the limit of sine, you get 0. That's pi cosine pi over x, yeah.